Hello, this is Dr. Stutzman, and today we're going to be talking about finding the arc length. So I've got a curve here that not don't have any straight lines. And if you had to find a length of something like this, maybe it was a river, you would probably do what I'm doing right now, just kind of find some straight line pieces, add up the length, find the lengths of those straight line pieces with a ruler and get the total length. Well, we're going to do the same kind of thing with calculus. So we're going to use integration to compute the length of a curved arc. And let's talk about how we can do this. So here's a curve, and like we said before, we're going to split it into little sections. We're going to find the length of each section. And right now, we're going to focus on just one of these sections. In this section, the straight line, the straight orange line, is not a very good approximation, but if we made it a little bit smaller, it looks like it'd be a better approximation. So let's look at that one in more detail. So here's this initial section. It's going for the ith section, we're going to go from some starting x to some final x, which gives us a delta x here. And there's going to be a change in y here. And how do you find the length of this straight line piece? We use the Pythagorean theorem, and it'll be this square root of delta x squared plus delta y squared. And I put a delta y sub I, because we're going to assume that each part of the curve is going to have a different change in y. And that's going to be our approximation of what the blue piece is. So let's look at this calculation a little bit more. And that's going to be, for just this one little piece, it'll be the square root of delta x squared plus delta y sub I squared. I'm going to add them up over all of the i's, all of the little pieces we broke it up into. I'm going to do some algebraic manipulation. I'm going to factor out a delta x squared. And what's left, if I pull it out, that'd be a 1, because delta x squared times 1 is delta x squared. And the next term will be delta y sub I over delta x squared. So these guys are the same if we distribute. And the first piece, if I take this, I'm going to factor this out. If I take the square root of something squared, as long as they're all positive, it's just going to be delta x. So I'm going to get the sum from I equals 1 to n of delta x times the square root of 1 plus delta y sub I over delta x squared. I'm going to take this delta x and move it to the right side. And if I let this delta x get very small, then these guys are going to become a very small differential dx, and this becomes dy over dx. And I can turn that into calculus, and that'll be the integral from the beginning to the end of the square root of 1 plus dy over dx squared times dx. And dy over dx is better known as the derivative, or f prime of x if our function is f of x. So our approximation is this formula we have here. Now, this is a pretty simple calculation. It's good to memorize. You could go and derive it without much difficulty by going back like I just derived it earlier. But let's take this and use it. So the integral that looks simple, sometimes it's hard to solve. We're going to do one example that we could do by hand. So calculate the length of the curve. We rewrite the formula for arc length. The integral from the beginning to the end of the square root of 1 plus f prime of x, that part squared dx. All right, so my curve is f of x equals 2 times x to the 3/2 power, which looks like this. And I just want just the piece that's between 0 and 1. So it looks almost like a straight line, but it's definitely a little bit more curved at the bottom of it. So here is that curve between 0 and 1. So what is f prime of x? Well, from the power rule, bring the 3/2 out front. So it's 2 times 3/2, reduce the exponent by 1, which gives me 1/2, or 3 times the square root of x. So we're going from 0 to 1. So arc length would be equal to the integral from 0 to 1 of the square root of 1 plus 3 square roots of x squared dx, which is 1 plus 3 squared is 9. The square root of x squared is x, as long as x is all positive, and it is between 0 and 1. All right, the way we're going to find this integral is we're going to do u substitution. U is 1 plus 9x. So du is 9 dx. I don't have a 9 dx, but I can make a 9 dx by multiplying and dividing by 9. And I'm going to change the limits of my integration and get rid of my x's and only worry about u's by itself. When x was 0, my lower limit of integration, u is equal to 1 plus 9 times 0, which is 1. When x was 1, which is my upper limit of integration, u will be equal to 1 plus 9 times 1, which is 10. So after I do my substitution, I now have my integral of 1/9 times the integral of from 1 to 10 of the square root of u du, which is 1/9 times, so this is the same as u to the 1/2 power. So I use the power rule, raise the exponent by 1, divide by the new exponent between 1 and 10. So I get 2 27ths times 10 to the 3/2 minus 1 to the 3/2. Which is approximately 2.268. Now, if I would have gone and just did a straight line between 0, 0 and 1, 2, this is a triangle, a right triangle, 1 for the base and 2 for the height, which makes the hypotenuse a square root of 5. And if I approximate, this is 2.36. So they're close to each other, but not exactly the same. So 2.236. So they're off by about 1%, 1.5%. Let's do another example. Set up but do not solve an integral formula for the arc length of sine over 1 period. So here's what sine looks like. And for just 1 period, that's the piece for 1 period. So it's a bit more curvy. We're trying to find the length of this curve. From one period, which is from 0 to 2 pi. So my f of x is sine of x. F prime of x is cosine of x. One period, I'm going to start at 0 and end up at 2 pi. Arc length formula is the integral from the beginning to the end of the square root of 1 plus f prime of x squared. As often is the case in arc length, this is not a integral that we can do by hand with using the tools we have right now. This is not a Pythagorean identity. If it was 1 minus cosine squared, we'd be able to do it, but 1 plus cosine squared doesn't work. So we're just going to leave it like this, which seems like we're giving up. But this expression will give us the answer, and we can find that answer by putting into your calculator and find out what the answer is. It'll give you a decimal approximation. All right. The last one I want you to try by yourself. Find the length of this curve, f of x equals 3 minus 2x. It's not a very curvy curve because it is a straight line. That's y-intercept of 3 and a slope of -2. So I want to find the length of that curve between 0 and 2, which I think that's where 2 is down here. Find the length of that curve by using both the arc length formula, which you're going to have to, the arc length formula once again is the integral from the beginning to the end of the square root of 1 plus f prime of x, the quantity squared, dx, or use Pythagorean theorem because this is a straight line. And you should get the answer of 2 times the square root of 5 units. All right, thanks for coming along, and we'll talk to you next week.